So all along we've been doing interpolation, and we solved questions under the direct method of interpolation as well as the Lagrange method of interpolation. Now in today's lesson we are going to look at another type of interpolating method, which happens to be one of the most popularly used interpolating methods, which we call the Newton's divided difference polynomial method. Now in this lesson we are going to solve this problem using the first order interpolating polynomial as well as the second order interpolating polynomial. So let's get started. So the general form of the Newton's interpolating polynomial is given as fn of x, and that is said to be equal to b0 plus b1 times x minus x0 plus plus bn times x minus x0 times x minus x1 x minus xn minus 1, where b0, b1 through to bn are said to be coefficients. Now these coefficients can be determined or evaluated by combining the data points that have already been given to us in the problem, including the equations that we find below. So we combine the data points and the equations we find below in order to find or evaluate b0, b1 through to bn, which are the coefficients. So for the first equation, we have b0 equals f of x0. We have b1, that is the second one, b1 equals f of x1 x0 in a square bracket. We have b2 equals f of x2 x1 x0 also in a square bracket, through to bn equals f of xn minus 1 x1 x0 also in a square bracket. Now the bracketed function evaluations are said to be finite divided differences. So for example, for f of xi xj, that is in the bracket, that is said to be equal to f of xi minus f of xj, all divided by xi minus xj. Now this is said to be the first finite divided difference. And then also we can have f of xi xj xk also in a square bracket, and that is said to be equal to f of xi xj in a square bracket minus f of xj xk also in a square bracket, all divided by xi minus xk. This is called the second finite divided difference. Now you realize that at the numerator for this and then for that, this has been represented in the simplest form. Okay, so if you want to expand this, then this is the same as what we have here. So you can just fix this here, and then you do same for this one, and you realize that you are going to obtain something very complex. Okay, but then this is the simplified form of the expression, or better still, for this particular function. So in effect, we are going to use the equations we have below as well as the data points that have already been given in the problem to find the coefficients b0, b1 through to bn. And then out of that, we are able to generate an expression for the required polynomial function of order n, which we are going to use for whichever estimation we are being asked. So in that regard, let's consider the first problem. So in the first problem, we have this data set, and then we are asked to determine the value of the velocity, or better still, to estimate the velocity at t equals 16 seconds using a first order polynomial interpolation by the Newton's divided difference polynomial method. So let's try to solve this problem together. So notice that in this problem, we are going to solve this question using the first order polynomial. What this primarily means is that we have the order n to be equal to 1. Now since we have n to be equal to 1, it means that we are going to have n plus 1 data points. So in other words, we are going to have 1 plus 1 data points, which is 2 data points. So we have 2 data points. We are going to come back to this later. So 2 data points. So having order n equals 1, we are going to generate the velocity function. Okay, so now let's come back to the general form. We have fn of x. Okay, this is a function of x. So here we have n to be the order. So this time we have velocity, okay, v of t. So it means that we are going to have we have n to be 1, and then it's a function of t. So we have v1 of t, and that is basically going to be, because we have a linear function, or we are dealing with a linear function, that's basically going to be b0 plus b1 into bracket t minus t0. That is from the general form of this equation. So b0 plus b1 into bracket t minus t0, okay, for the linear function. So that is what we have here. Now the next thing we want to do is, from the previous lessons you realize that we need to take two values of t, or two values that are very close to 16, because we want to estimate the value of the velocity at t equals 16 seconds. So we want to select two numbers that are very close, or that are closest to 16, but then they also bracket 16. And then from the previous lessons you realize that we chose the values 15 and then 20. So we have t0 15 seconds, and then t1 also to be 20 seconds. Now for all these two time values we have their corresponding velocities, and so we have v of t0, that is 362.78 meter per second, and then for v of t1, that is this one, we have 517.35 meter per second. So these are the respective velocities for the time t0 and then t1. So the next thing we are going to do is we are going to combine these two, that is the data points as well as the equations, to obtain the coefficients b0 and b1. So let's do that here. So for the first equation, we have b0 equals f of x0. So we have b0 equals f of x0, and in our case we have velocity as a function of time. So we are going to have v into bracket t0, and thus we have b0 to be equal to, now the value of v of t0 is 362.78. so 362.78. so this is the value of b0. This is the value of b0. Now let's move on to b1. So for b1, that is the second equation, we have b1 equals f of x1 x0 in a square bracket. So we have b1 equals f of x1 x0, and this is equal to v of t1 t0. So from here we are able to express this as v of t1 minus v of t0, all divided by t1 minus t0. That is from the first finite divided difference. From this formula we are able to expand v of t1 t0 in a square bracket. So that is the expanded form of it. So let's basically put in the values. So here we are going to have v of t1, that is 517.35 minus v of t0 362.78, all divided by the time values. You have 20 minus 15. Now when you compute this, then you are going to have 30.8 30.914. So that happens to be the value for b1. b1 is equal to 30.914. So from this, then we can have the velocity function, that is v1 of t, and basically that is equal to, from this function, from this expression, we have v1 of t to be equal to b naught, that is 362.78, plus b1, that is 30.914, into bracket t minus t naught. T naught is 15, so we have 15 here. So next we can try to expand this. Okay, so we have 362.78 plus now 30.914 times t, that becomes 30.914 t, and then you multiply 30.914 times 15, and then you are going to have 463.71. okay, so you combine like terms, these two, and then you are going to have negative 100.93 plus 30.914 t. So this is v1 of t, okay, where 15 is less than or equal to t is less than or equal to 20. So realize that this is the same expression that we obtained when we were doing direct methods of interpolating, and then we considered the first order polynomial. We obtained this same expression for the velocity function. So from this, we want to find v1 of t at t equals 16 seconds. Okay, so we say for v1 of t at t is equal to 16 seconds, we have v1 of 16, and that is equal to negative 100.93 plus 30.914 times t, and that is 16. So you compute this, and then you have 393.694, and then this is nearly equal to 393.69 meter per second. So this is the value of the velocity at t equals 16 seconds. So we say that v1 of t is nearly equal to this value at t equals 16 seconds. So now let's consider this same problem using the second order polynomial. So for the second order polynomial, here we have n to be equal to 2, which means that we are going to have 3 data points. So in that regard, we are going to have the velocity function to be, this time we have v2 of t, okay, and that's going to be, from here we are going to have b naught plus b1 into brackets x minus x naught. So let's write that first. So b naught plus b1 into brackets, we have t minus t naught. We have a function of time, so that becomes t minus t naught, plus b2. So here we have, for n equals 2, we have bn into brackets x minus x naught, x minus x1. So you realize that ours is going to be b2 times t minus t naught, t minus t1. So basically this is the velocity function that we are trying to obtain. So at this point, we are going to combine the equations and the data points in order to find the coefficients b0, b1, b2. So for the time values, or for considering these 3 data points, we need to select 3 points or 3 values of t that are closest to t equals 16, and that's bracket t equals 16. Now from the previous lessons, we selected t0 equals 10 seconds, t1 equals 15 seconds, t2 equals 20 seconds, and for all these values we have the respective velocities attached to them. So to find the coefficients, first of all we have b0. So b0 is said to be equal to f of x0, which is v of t0. So here, let's write that here. Okay, so it makes everything simple for us. This becomes 227.04. So this is the value of b0. Okay, this is the value of b0. Now let's move on to b1. So b1 is said to be v of t1 t0 in a square bracket, and then from the previous section you realize that this is equal to v of t1 minus v of t0, all divided by t1 minus t0. So fixing in the values, we are going to have 362.78 minus 227.04, all divided by 15 minus 10. Now when you compute this, you are going to have 27.148. So this happens to be the value for b1. This is the value for b1. Now let's move on to b2. Now to find the value of b2, we are going to have b2 to be equal to, so this time b2 is going to be v of t2 t1 t0 in a square bracket. So basically that is going to be from here, it means that we are going to obtain v of, in square brackets, t2 t1 minus v of, in square brackets, t1 t0, all divided by t2 minus t0. Okay, now the next step, we want to expand this. So here we are going to have v of t2 minus v of t1, all divided by t2 minus t1. Okay, minus, now for this part, that is v of t1 t0, that has already been evaluated here, and we got b1 to be 27.148. so we just fixed the 27.148 here. Okay, so we have this all divided by t2 minus t0. So from here we can have something like this: v of t2, let's come back here, that is 517.35. so we have 517.35 minus v of t1, 362.78 all divided by 20 minus 15, so minus 27.148, all divided by 20 minus 10. Now when you compute this, then we are going to have B2 to be equal to 0.3766. So we are going to have B2 to be equal to 0.3766. That's the value you are going to obtain for B2. So in that regard, we are going to have the velocity function to be V2 of t, that is this one, and that is going to be, we have B0 to be 227.04 plus B1, that is 27.148, so 27.148 times t minus, now the value of t0 is 10, so 10 here, and then plus B2, which is 0.3766 times t minus t0 times t minus t1, which is 15. So this is where 10 is less than or equal to t is less than or equal to 20. So at this point, we want to find the velocity at t equals 16 seconds. So we say that for v2 of t at t equals 16 seconds, we have v2 of 16, that is equal to 227.04 plus 27.148 times 16 minus 10 plus 0.3766 times 16 minus 10 times 16 minus 15. Now when you compute this, you are going to get 392.1876 meter per second. So that is v2 of 16. Therefore we say that v2 of t is nearly equal to 392.19 meter per second at t equals 16 seconds.